All right, so let's look at this combination circuit problem. So we have a simple circuit here, not super simple, but it's slightly simple, where we have a voltage source, the battery here, of 36 volts. We have a wire leading from the battery, in which we have connected some sort of resistor of mystery value, but we know there's 6 amps of current running through that resistor, and then that wire splits off into a wire that contains one resistor of 3 ohms, and the other wire has 2 resistors, each 2 ohms each, which both can join back into that battery. Quiet, Frisbee. Sorry, everyone, my dog is being a good girl. All right. So, looking at this problem, I'm going to list what I know. So I know I have a total of 36 volts. I know my resistor value 2 is 3 ohms. I know resistor 4 and 3 are also both 2 ohms. All right. And I know the current running through resistor 1 is 6 amps. All right, so this problem in a sense is a little trickier than the problems we've done before, because before I provided pretty much every single resistance value for you, but now we have a mystery resistance value. So, Frisbee. Sorry, my dog just was messing with my camera setup. All right. So, we can't find right away the total resistance. Right? So we're going to have to basically apply, to begin with, our loop rules and our junction rules, or loop laws and junction laws. So kind of looking here, we can logic through, well, if we know 6 amps of current is running through this resistor, well, our kind of working backwards, right, this didn't split off from anything. It's going to be the same current as running through our battery. So that's kind of the key in starting this problem. And after that, hopefully things kind of will fall through. So if you were working on this problem and you were stuck at the beginning, that's probably the thing that you were missing. All right, so my total current, which is the current running through our battery is also 6 amps. So then I can find my total resistance. So I take my 36 volts divided by my 6 amps and get a resistance of 6 ohms in total. Right? Now you can right away think, did we make a mistake? Because taking 3 plus 2 plus 2, all right, that gives us 7, which is more than 6 ohms. And then we still have another resistor. Is that an issue? It's not an issue, actually, because these are not all in series with each other. We have this resistor here, which is these elements here are in parallel with each other. So basically, we're going to have a smaller resistance because we have elements in parallel, and those add inversely. So in looking at this now we can calculate this missing resistance value. Right, so what I'm going to do is kind of chunk this into smaller and smaller pieces. So the first thing I can see here that's going to be really simple to do is replace these 2 resistors with one resistor of equal value. Right, and those are going to be easy to simplify since those resistors are in series with each other. Right, so here's kind of my new circuit. Sorry, it's kind of a not very neat sketch. This is our mystery resistor. We still don't know that value. This guy here has 3 ohms, and now my resistor of an equivalent value is going to be 4 ohms. Okay. Now looking further here, I see that these 2 elements are in parallel with each other, so I can add those together. So that we still have our mystery resistance value. So now we need to add these together properly. So 1 over our resistance is going to be 1 over 3 ohms plus 1 over 4 ohms. Okay. So 1/3 plus 1/4 gives us a value of 7/12. That's not our resistance value because that's 1 over our resistance, so we have to take the inverse of it. So we get 12/7. That's this resistance value. Right. So now we see we basically simplified our problem to be just this series circuit here. Right? Where, Frisbee, stop. So, where we have 2 resistors in series, and now we know our total resistance. Our total resistance is 6 ohms. So in adding 12/7 plus this mystery value of 6 ohms, I'm going to take that 6 and divide that by 12/7, and we get 30/7. I'm going to switch that to be a decimal, so I will have rounding error in my problem. So 30 divided by 7 gives us about 4.3, so I'm going to round to 1 decimal point. So resistor 1 has a value of 4.3 ohms. Well, now I know if I know the current running through that resistor and its resistance value, I can find the voltage drop over that resistor. So I take my 4.3 multiplied by 6, doing I times R, that's equal to V. That gives me a voltage drop of 25.8 volts just in this resistor, all right, which basically leaves me a total of, let's see, we take that 36 minus the 25.8, 10.2 volts to be dropped off in the rest of our circuit. So we can look at our loop law. So I'm going to follow, let's say we do the shortest loop. All right, so I leave the positive end of my circuit, basically following the current. Travel through this resistor where we drop off 25.8 volts. And then we can take one of two paths. I'm going to take the shortest path. So I'm going to drop off some amount of voltage here in this resistor and then travel back to the battery, which then we have to have 0 volts. Right? So then just by that logic, we can see that we have to have 10.8 volts be dropped off in resistor 2. By 10.8, I mean 10.2. 10.2 volts dropped off in this resistor, right? Since we have to have 0 coming back to the battery. Similarly, we can do a couple other steps in logic here. One could be like, well, this resistor is in a series, in parallel with these two resistors that are in series with each other, right? So that means we have to have 10.2 volts dropped off in the combination of these two. Okay? You can also realize that by using our loop law with the big loop. Okay? Well, dealing with that 10.2, right, we can see that these resistors have equal values, so they're going to drop off with equal voltage. So it's going to be 1.5 volts in each of them. By 1.5, I mean 5.1. I'm sorry, you guys. It's Friday afternoon, right after work, after a long week. All right, so we have 5.1 volts dropped off in each of these resistors. So then I can calculate the currents that we have going on. So the current running through resistor 2, this guy here is going to be our 10.2 divided by our 3 ohms, giving us 3.4 amps. Whereas in these two resistors, let's see, if we take 5.1 divided by 2, gives us 2.5, I'm going to leave that extra 5 here, amps. I'm going to check my work here by applying our our junction law. So if we have 6 amps coming in this wire here, I know the current coming out here has to add to this current and they have to equal 6 amps. So in this wire I have 3.4 amps, so I take my 3.4, add to it the current in this wire, which is 2.55. And that gives us 5.97, which is approximately the 6 I was looking for. Like I mentioned before, I am dealing with rounding error here. So that kind of, that checks through. So I basically have calculated all I want to do in this problem now. I will mention, I've mentioned this in combo problem number 2, that is also uploaded onto my YouTube channel. But in case you only looked at this problem here, you might be asking, well, what's going to happen if these resistors were 2 different values? So we can't use that jump in logic that the 10.2 volts is divided equally, because it wouldn't be. Right? So one way of doing it would be calculating using a ratio, but another way would be actually dealing with the current first. So we actually go first calculate the current running through this wire through resistor 2, when you calculate that being 3.4 amps, and then use our junction law that we have 6 amps coming in, so then we must subtract, so then the amount coming out has to equal that 6 amps, so this 3.4 plus the mystery current has to equal the 6, so then we would have calculated the 2.55 amps in this wire, and then be able to calculate the voltage in each of those resistors. Uh-oh. Well, I guess that's a good place to end.